The central limit theorem is really the most important theoretical result in all of statistics, and that's because it unlocks our ability to make an inference about the average value of some probability distribution that's generating our data without actually us having to care about what that distribution really is. And for the most part, that's very useful because a lot of times we don't really care what this data generating distribution is that we're dealing with, if it's normal, if it's Poisson, if it's negative binomial. We really just want to nail down, well, what's the average of whatever distribution's making our data? And the central limit theorem is a comment about this. Now, the central limit theorem is a theoretical result that talks about the sampling distribution of the average values of a random sample that we might collect. And so it's worth briefly reviewing what a sampling distribution really is. So when we talk about a sampling distribution, that is a comment about the possible values of some statistic, some numerical value that we might calculate from a sample, and the relative frequencies of those values. As a very simple example, let's consider taking a random sample of size 3 from the following PMF. Basically, we are going to observe values of either 1, 2, or 3, each of which have equal probability. So our sample might consist of all 1s, a mixture of 1s, 2s, and 3s, maybe all 3s. And let's talk about the sampling distribution of the specific statistic, the sample mean, the average of our sample values. So what the sampling distribution of the sample mean is referring to are all the possible values that we might measure for the sample mean when we go and collect data and the relative frequencies of each. And in this case, we can go through and just exhaustively enumerate every single possible way that we might end up observing our sample values and just look to see what the averages are for each of those. So it might be the case that all 3 sample values happen to be all 1s. We might have the first 2 values being equal to 1, the last one equal to 2. We might have the first 2 values equaling to 2, the last one equaling to 3. We might have the first and third equaling a 3, the middle value, the second value being equal to a 2. And so what we see are all the possible ways that we could observe the first, the second, the third data value, and the averages for each one of these potential samples that we could observe here. So the sampling distribution just says, okay, well, what are all the possible values that we might see for this sample average here? We might see a 1, we might see a 4/3, we might see a 5/3, etc. And then what are the possible frequencies, the probabilities of each one of those? And so here we have a frequency table. Here consists of all of the possible values for the sample average that we might observe, the 1, the 4/3, 5/3, 2, etc., and the probabilities of observing each one of those values. So there's only a 1 in 27 chance of observing a sample average of 3 because that would consist of having all 3 of those sample values equaling to 3 here. But there's a pretty good chance, a 7 out of 27 chance, of having a sample average of 2. There's a lot of different samples that actually result in a sample average of 2 here. So the sampling distribution of the sample average in this case consists of these 7 potential values with these respective probabilities. And so when we talk about the sampling distribution of a statistic, it's just the possible values of that statistic that we might observe when we go and collect data along with the relative frequencies of each one of them. And actually, we've been talking about sampling distributions really throughout the whole semester here. When we were talking about the binomial distribution, well, the binomial distribution actually is the sampling distribution of the sum of a random sample of Bernoulli random variables. Now, if you remember the Bernoulli distribution, we only observe 2 possible values, a 1 or a 0. Typically, we associate a 1 with a success, like a customer clicking on an ad, and a 0 is a failure, like a customer not clicking on the ad. Success has probability p, failure has probability 1 minus p, and when we use that binomial distribution, we were counting up the total number of successes out of n trials. Well, if our random sample is a collection of those 1s and 0s, then the sum of those 1s and 0s is essentially counting up the number of successes out of n trials. And so the sum of all of the x's in that random sample is a binomial distribution. That's going to be the sampling distribution of the sum of those random values in our sample. Likewise, we've talked about the geometric distribution, counting up the number of failures that we observe until that very first success. So if we hone in and look at that statistic, basically the minimum value of I among all of those values of I where we see x equal to 1, well, that is related to that geometric distribution, basically the trial on which that very first success occurred. And we've been talking about the sampling distribution of the possible values of p hat we might observe when we go and conduct a Monte Carlo simulation. We've talked about how the possible values for p hat we might observe is well described by a normal distribution with a predictable peak and also a predictable standard deviation. And in the last unit, we talked about the sampling distribution of theta hat MLE. So when we go and collect data, it's unlikely that the value of the MLE that we might measure from that sample matches up exactly to what theta is, but it's going to be close. And we've talked about how the sampling distribution, the possible values for theta hat that we might measure, is approximately normal as long as we're dealing with a large enough sample, with a predictable peak and a predictable standard deviation. And so we're actually kind of used to talking about what the sampling distribution is, and so the central limit theorem is going to help us out here. So this central limit theorem is a comment about two different statistics, either the sample average that we might measure when we go and collect data, or the sum of all the sample values. And here's what the central limit theorem tells us. It tells us that regardless of what the probability distribution is that's making our data, if it's discrete, if it's continuous, if it's normal, exponential, Poisson, zero truncated Poisson, negative binomial, etc., the possible values that I might measure for the sample average, or that I might measure for the sum of all of the sample values, actually has some pretty predictable properties. If the average value of that probability distribution is mu, and the standard deviation of that probability distribution is sigma, regardless of what that distribution is, I can actually make a pretty strong statement about what possible values for the sample average that I might observe when I go and collect data, or the possible values for the sum of all the sample values are when I go and collect data. The sampling distribution of either one of those statistics is approximately normal with predictable properties and all related to the value of the expected value of that probability distribution, regardless of what it is, or the standard deviation of that distribution as well, mu and sigma here. Now, I think the best way to really understand this is just with a visual demonstration. So I'm going to bring up my central limit theorem demo here that was written on Shiny, just to really hit this message home and to talk about what the implications are for the central limit theorem. So here we're dealing with a probability mass function that's making our data that is relatively simple. This PMF only has three possible values, x of 1, 2, and 8, and each of these three values are equally likely. Now, the central limit theorem is a comment on what the possible values for the sample average might be when I go and collect data. And so let's look at an example where I'm just considering samples of size 2. So I might observe 2 1s, 2 2s, 2 8s, or a mixture of these quantities here. Well, what is the sampling distribution of the sample average in that case? Well, I might get an average value of 1 if both those data values happen to be 1. I might get a value of 1.5 if one of the values is 1, the other is 2. And so each one of these little lines here represent the possible values for the sample average of size 2 that I might observe. And so this would be my sampling distribution of that sample average. We'll talk about what this red line is here in a second. But as I think about samples of different sizes, well, increasing that sample size is going to increase the variety of the possible sample averages that I might observe when I go and collect data. And so if I were to consider all possible ways I could potentially collect a sample of size 15, all these bars here represent the possible sample averages that I might end up observing and their relative frequencies. So I might observe a value of 1 if all 15 of these values happen to work out to be 1, but we see that's relatively unlikely. Chances are I'm going to get a sample average of maybe around 3, 4, maybe up to 5 or so. But the shape of the sampling distribution looks a little bit wavy. It's kind of crazy here, indicating that based on the structure of the PMF, the specific values that I might observe in my sample themselves and their relative frequencies, the possible sample averages kind of has a very complex and kind of interesting shape in this case, this very wavy shape. What the central limit theorem is talking about is what happens to the shape of the sampling distribution of the possible sample averages as I start increasing my sample size, as I start thinking about samples with increasingly more values. And let's just see what happens. As I go and increase the sample size from 15 to say 27 here, consider all possible ways I'd collect values of 1, 2, and 8 for sample sizes of size 27. What happens is that the shape of the sampling distribution of the possible sample averages starts to look more and more like a normal distribution. And in fact, that's what this red curve is. This red curve is what the normal distribution is based on the central limit theorem. So the central limit theorem says that as long as we're dealing with a large enough sample, the possible values for the sample average that I might observe in those random samples is going to look approximately like a normal distribution, with a peak at mu, whatever the average value is of the probability distribution making my data, and with a standard deviation equal to sigma over the square root of n, where sigma is that standard deviation of the probability distribution making my data. And so from this demo, what we see is that, yeah, as we start increasing the number of values in the random samples we're considering, the shape of the distribution that's describing the possible averages that we might observe from those random samples is starting to look more and more and more like a normal distribution. And not just any normal distribution, but the normal distribution that's suggested by that central limit theorem. And now here's really the remarkable thing about the central limit theorem is that this is true regardless of what the PMF or PDF is that's actually generating our individual sample values. If I change this PMF to freeform right here, let's just take a look at another example. So I'm going to go and look at this PMF right here. So what we see is it's rising to a peak right at around 2, values larger that are a little bit less likely to be observed. Let's see what happens when we deal with samples of size 2 from this distribution. Both might be zeros, both might be 11s. We might get a mixture of values between 0 and 18 here. So if I consider all possible samples with just 2 observations in them, here is my sampling distribution for the sample average. These bars represent the possible values for the average that I might see, and the heights of them represent the probabilities of each one of those averages. And what we see is that the overall shape kind of looks like a normal distribution. The red curve is what the central limit theorem suggests, and there's a bit of a mismatch here, but the central limit theorem is really only applicable to large enough samples where I'm collecting enough data values here. And so let me just bump up that sample size. Let's consider all samples of size 10 here. So when I consider all possible ways my sample could have turned out that contain 10 data values here, so a good mixture of zeros, 6s, 17s, 18s, everything in the middle here, I'm seeing that the sampling distribution of those possible sample averages is matching up pretty darn closely to what the normal curve that the central limit theorem suggests. And in fact, if I bump up that sample size by quite a bit, if I consider all possible samples of size 50 that I could potentially observe, I don't really see a difference at all between the sampling distribution of those possible values for the sampling distribution or a sample average that I might observe when I go and collect data, and what that central limit theorem is suggesting. Let me go and actually zoom in on around where the peak is. You can see there's a little bit of a discrepancy, but it's pretty darn close. Going up to samples of size 100 here, we see that we pretty much have almost an exact match. That central limit theorem is in full effect. The central limit theorem is predicting essentially exactly what the distribution is for the possible sample averages that I might observe here. And so that's going to be the remarkable thing about the central limit theorem. If I change the shape of the probability distribution that's generating my data, I'm going to see the same result again and again and again. Let's kind of look at a very skewed distribution here. Let me get it as skewed as I can possibly get. So a big old peak at 0, larger values progressively less likely to be observed, but still some chance of observing an 18 here. Notice that for samples of size 27 in this case, there's a rough correspondence between the distribution of the possible sample averages that I might observe and what the central limit theorem suggests I should see. But as I increase the sample size in these samples I'm considering, what I'm finding is a closer and closer correspondence to the sampling distribution of those sample averages and what that normal curve suggests I should be seeing from the central limit theorem. And in fact, if I'm looking at all possible samples of size 100, there's a relatively little discrepancy here now between the actual sampling distribution of those sample averages and what the central limit theorem suggests I should be seeing. Let's look at kind of another weird distribution here. Let's look at one that's bimodal, kind of a peak at small values, a peak at large values here. And we see that by the time I'm considering samples of size 30, there's really no discrepancy whatsoever between the distribution of the possible sample averages that I might observe when I go and collect data and that normal curve that the central limit theorem is suggesting. And so this is really what the power is behind that central limit theorem is letting us know here. Its central limit theorem is essentially saying that regardless of what PMF I'm dealing with, regardless of what distribution is actually generating my data values, I can actually predict fairly well what the possible values for the sample average that I might see when I go and collect data. It has a very predictable distribution, and it's tied in very strongly to what the average value is of that data generating distribution and its standard deviation. So the upshot is I don't actually really need to know what is making my data here, if it's Poisson, if it's binomial, if it's normal, if it's exponential, if it's Weibull. I'm going to get the same results regardless. The sample average that I might observe when I go and collect data is a very predictable amount from what the averages of the probability distribution is that's making my data. And so this central limit theorem is going to allow me to unlock an ability to come up with a confidence interval for the average of whatever distribution is making my data without actually knowing what that distribution is.